All right, this is Physics 1A for Wednesday, May 27th, and today we're going to be talking about an orbital transfer, and we're going to talk about dark matter. Maybe we'll talk a little bit about black holes too. So we've been talking about gravity, and we've been talking about things that orbit, and some of the things we've learned so far are about what the force of gravity is. Last time what we learned was about the potential energy due to gravity when you have something that's in orbit, and that potential energy is equal to basically negative gravitational constant multiplied by the mass of one body. There's always two bodies involved in a gravitational interaction, so you need two masses, and you divide by the distance between their center of masses. That's the potential energy of a gravitationally bound system. I think that's mostly what we need to know here. The other thing we need to know is that for objects that are orbiting one another, there's basically two rules that we can follow to understand what's happening. One is that angular momentum is conserved within orbits, and one is that mechanical energy is conserved in orbits. Okay, and we're going to use those both to understand some things today. All right. So this is the problem here that we want to do. And it's kind of a tricky problem. Maybe some of you guys have already looked at it. It's been kind of on the notes for the last few days. I just haven't had a chance. Maybe if I zoom out or I'll just make this a little bit smaller. And zoom back in. Okay. Do you guys have any questions about anything else before we get started on this? Okay, so here's the problem we want to look at. It says a 10,000 kilogram space capsule is to be returned to the Earth from the Space Telescope, which is in a circular orbit at an altitude of 12,800 kilometers. It's desired to have the capsule leave tangent to its orbit at A, here, and arrive tangent to the Earth's surface at P, here. So this body right here, that's the Earth, and there's basically two different orbits that we're looking at here. So the capsule itself is currently on the Space Telescope, and this outer curve right here represents the orbit of that Space Telescope. Okay, and it's a circular orbit. It's an altitude of 12,800 kilometers. Right. The goal is to take this space capsule, right, and get it to be returned back to Earth over here. So the way you can think about this is that currently, let me draw a couple pictures here. So let's start off. It's like this is the Earth. Okay, that's the Earth. Okay, and then we've got two different orbits here. So one orbit is out, let's say kind of like this. I thought that would put that right in the center. I guess that's good. Here, is it lining up like? So that's the orbit of, this is like what is this called? Space Telescope. Okay, so this is the orbit for the Space Telescope. Call it ST orbit. So it's a circular orbit, and it has this altitude of 12,800 kilometers, and that's going to be above the surface of the Earth. So we've got our satellite right here at point A, and we basically want to do something with our satellite so that we can get it from here to go onto an elliptical orbit, so that something like that. Let's see how that shapes up there. Need to make it a little bit smaller, I think. We want it to go on an elliptical orbit like this, basically. Here, like that. So it's like, it's on the orbit, it's basically orbiting around with the space shuttle, or with the Space Telescope, right? And, it's keeping going around and around and around, kind of constantly falling toward Earth, but never quite getting there, going in the circular orbit. And we want to do something at point A to basically reduce its speed so that it can fall naturally on this path back down to Earth, okay? Alright? Does that make sense? This is what we want to do here? So it says, find the required speed of the capsule A, at A, VA. Find the speed of the Space Telescope, VS, and then we need to do some other things here. But the goal is to figure out what speed do you need to have right here for your little Space Telescope, or for your shuttle. So the speed right here we're going to call V sub A. And that's really what we're trying to figure out. What speed does it need to have to get back to this point? Alright? Does the problem make sense to you guys? Alright, so in order to do this, what we're going to do is apply these concepts above, and let's just shift over just a little bit here. Let's move this maybe down like that, and then just like shift over to the right a little bit, so we can still see the problem and the picture that we're looking at. So there's two things that we can say about this. First of all, we know that it's going to have some velocity over here, but it's also going to have some velocity when it gets to this point right here. And that velocity is going to actually be much higher. Its velocity here, we're going to call the velocity at point P. A basically stands for the apex or apogee of the orbit, and P stands for the perigee, or the closest point of the orbit. Right? We don't really know what either one of these are, so we basically just have these two unknowns, right? The information that we do have in the problem we can like label over here. One is that this telescope right here has a mass m, and that mass m is equal to 10,000 kilograms. And then we know the altitude of the orbit is 12,800. So what I want to do now is I want to say, okay, well then there's going to be a line that we can draw from basically the center of the Earth. And that line right there, which goes from the center of the Earth out to point A, I'm going to call that R sub A. And I'm going to say that RA is going to be equal to... Well, what's it going to be equal to? Can you guys tell me? What do I need to do? If it says that this is the altitude, what do I need to do with that number? If it's just the altitude, and I want to find the distance from the center of the Earth up to that point, that number plus r, where r is what? The radius of the Earth, right? So you have to add to this the radius of the Earth. And the radius of Earth is about 6,400 kilometers. Right? Which means that RA, I think, is 19200 km. Is that look right? 2 plus 6 is 8, and you have to add that 8, yeah. That's RA. And then I'd also say that there's also going to be another distance on here. I don't have to label it, but since it says it's desired to have the capsule leave tangent to its orbit at A and arrive tangent to the Earth's surface at P, you know, that means that its distance on this side to the center of the Earth, let's use yellow or something for that from there to there, that distance is basically just the radius of the Earth. And we're going to say that's basically equal to what I'm going to call R sub P. And R sub P is going to be, you know, obviously just the radius of the Earth, 6,400 kilometers. Okay. I think that's all the information we need to solve this now. I guess we need the mass of the Earth, too. So now, in order to find what VA is and what VP is, we effectively have to use the two constraints that I said. One is that angular momentum is constant within an orbit. So if we take the angular momentum basically at point A, which would be what? It'd be the mass of our object times the velocity at point A, which is VA, multiplied by the distance from here to here, which we're calling R sub A. Then that's going to be equal to the mass of the object times the velocity at point P, multiplied by the distance to point P. Guys have any questions about that? We can kind of simplify this too a little bit. We can say, well, we can cancel this mass, we can cancel this mass. And we know what RA and RP are. Our goal is to find VA. So what I would say is we can write this like this. We can say basically V sub P is going to be equal to V sub A multiplied by RA, and then we just divide by RP. But if you look at the way this works out here, if I take RA over RP here, I think it's a ratio of like 3 to 1 or something like that. I'm pretty sure this is going to be something like 3 times VA is equal to VP. Can you guys check that real quick and see if that looks right to you? If you plug in RA over RP here, do you get 3? You guys have any questions? Alright. The next thing to do is to use the energy conservation statement to say that the mechanical energy of our orbit is going to be constant. And so the initial energy of our orbit is going to be basically its kinetic energy at point A. So we'll basically do point A here and we'll do point P here. So it's going to be 1/2 mass of the object, not the Earth, the mass of this capsule, times VA squared, plus negative big G, little m, big M, divided by RA. That's the energy at point A. And then the energy at point P is 1/2 mass times VP squared minus G M divided by RP. You guys have any questions about that? Alright. So now our goal is basically just to solve for our one remaining unknown. Since we have this relationship right here, we can basically eliminate every unknown except for one velocity. Okay. Our goal is to find VA, so we're just going to replace VP with VA. Okay. Let's start doing that. So let's group some things together here. There's a mass in every single term, right? So this all cancel out, and we do a little algebra here. We're going to have something like 1/2 times VA squared minus VP squared. I'm basically just going to subtract this term over to the left-hand side. Should be equal to this term and this term both have G and M in them. So what we're going to do is we're basically going to factor out G times big M and say that's multiplied by 1/RA minus 1/RP. You guys follow the mathematics there? Just algebra. I kind of skipped a step or two though, so just wait a second, see if you agree with that. Basically think about adding this term to the right-hand side, leaving this term the way it is. Okay, and now you pull this right here. 3VA is equal to VP, so we can do even more. We could also say here that, what is it, RP is equal to, or 3 times, I think we could also say this. 3 times R sub P is equal to R sub A. We can make that replacement too if we really wanted to. So if we did that, this is what we're going to get. So we'll have here, I'm going to move the 1/2 to the right-hand side. So we're going to have, what is this, VA squared, stays the same, minus VP squared is going to be 3VA squared, right? One over RA is 1/3 times RP. And then we can do stuff like this right here becomes -8 VA squared. On the right hand side, this is 1/3 minus 1. So what is that? -2/3. So something like -4 GM over 3 RP. Does that look right? What do you guys think? Does that look okay? Have I lost you? You guys following this at all? I'm like confused, or it's just too simple, or what's going on? So let's make sure I'm not making any kind of mistake. Anyway, all right. So then, solving this for what VA now? Let's see. VA is going to be equal to, let's see, -4 over -8. That gives you a half. So it's basically going to be something like the square root of big G M over 6 RP. I want to say. I think that's right. And by the way, big M here, I for sure said big M is the mass of the Earth, my bad. Mass of the Earth is about 6 times 10 to the 24. Alright, so then we plug everything in here. We're going to get the square root. 6.67 is big G. Times 10 to the -11. And that's in units of newtons times meters squared divided by kg squared. Mass of Earth is right above right there, so it's 6 times 10 to the 24. That's all divided by, square root goes all over this stuff, the 6 times RP, and RP is equal to 6,400 kilometers, so that would be 6.4 times 10 to the 6th. And then if we go to our calculator here, and we look up put the top on this thing. If you guys want to calculate that for me, go for it. Remember to use like the EE button on your calculator to get exponential notation. Just waiting for this calculator to load up. It always takes a long time. So we want to calculate again, if you don't remember, this basically is 6 times 10 to the 24. This thing means times 10 to the, or basically just says 6, and this is the exponent of the 10. Divided by 6, and then divided by 6.4 d6. And we raise all of that to the 1/2 power. 3228. That's what I got. Is that what you guys got too? Here we go. Okay, so next thing to do is to solve part B. That's basically part A. Part B says to find the speed of the telescope Bs. So the telescope is cruising along. Let's put our telescope in here. Kind of satellite. And it's got a velocity at any moment in time that we call v sub s, velocity of that space telescope. And that's what we want to calculate. Now this is a little easier. One of the things that we proved at some point is that the velocity of a circular orbit, and this is included within well, we derived it in class, but it's also on the equation sheet for gravity on the packet that I gave you guys. I think this is what it is. I think this is what it is. Where in this case, r is going to be this distance. Oh wait, well, it's the same as RA, isn't it? So this is actually going to be r sub a, right? Because that's the orbit. The circular orbit has the same, you know, if you look at it this way, that distance right there is r sub a as well, right? Is that right? Did I write that right? Do I need to get my notes and check? Or does that look right to you guys? Can you check for yourself on the notes? On the packet that I gave you? Long ago, if you still have it. Oh, my 1C notes, my 1A notes all mixed together. Oh, there it is. Alright, so the velocity of the circular orbit, yeah, it's the square root of g over r. Okay. You derive that by using what you know about circular motion and the gravity force between the two objects. Just equating, you know, force to mass times acceleration. You can prove this right here. So the velocity of a circular orbit, then, in this case, what we're calling, you know, Bs, is going to be the square root of, again, 6.67 times 10 to the negative 11. Times big mass, which is 6, that's the mass of the Earth again, 6 times 10 to the 24. Divided by RA, which is right here. 19200, so that's, I think, 1.92 times 10 to the 7, I think, meters. And we screwed all of that, and again, this Voyager goes over everything. I think here we'll get VS, and I have a question. Do you guys think this is going to be faster or slower than VA? Make a prediction before we calculate it. Well, maybe you could just look at the two equations and see what the relationship is. But what do you think? Is it going to be faster or is it going to be slower than? What do you think? Bigger, faster. Okay, let's see. So go back to this guy, and we're doing. 4565. So as you guys predicted, it's going to be bigger. 4565. You actually wrote in the chat. Nice. So that's part B. All the stuff in black was part A. This last statement is misleading. So first of all, we want to figure out if the thrust of the engine is 10 to the 5 newtons, find the burn time required. That would be to say the shuttle is moving with this speed, and we need it to get to that speed right there. We need to basically slow it down, right? Because it's going in the circular orbit out here. You can kind of think about how this is working. It's falling around, falling around, falling around. It would basically just stay with the... It would stay with the satellite, the space telescope. The capsule and the space telescope would be riding along together, right? Just doing these loops. And it would go on forever, basically. But once we get to this point right here, at point A, if the satellite, or the, sorry, if the capsule, if it slows down and it drops its speed to this, it can basically go back to Earth, you know? So the question then is, if the thrust of the engine is 10 to the 5 newtons, find the burn time required. Like, how long would it need to turn its engines on, right? How long would it need to turn the engines on in order to basically kind of make this maneuver? Sometimes they call this delta V, the change in velocity needed to kind of fall back to the Earth when they talk about orbital mechanics. So let's calculate what it would be. Alright, so to be clear what's going on here, the idea is that you have this object and it's traveling in this direction with some velocity that we call v sub s, and you want to make it slow down so its final velocity is going to be less than that. It's going to be the VA velocity, right? And that's going to occur by effectively exerting a force in the opposite direction on our capsule, right? So if you exert a force back this way, this would be like our thrust. Wait. Yeah. The idea would be you'd basically take your rocket and you'd aim it this way, right? And you'd fire your thrusters back this way, which would exert a force on the rocket like that we could call T or something. You know, you shoot hot gases out the back, and it has the effect of basically changing the momentum of this object, and that's what we want to figure out. Any questions? Yeah, we want to slow it down, right? If we want to slow it down, we need to have an acceleration that points opposite the direction of the velocity, right? Thrust and the acceleration would be in the same direction, but they need to be opposite the velocity, right, to slow it down? Wouldn't that slow down? Right? Okay, cool. It's a little bit misleading because you think, I don't know, maybe you think like if the rockets go that way, the thrust is in the same direction or something. I kind of see where you're coming from, but it's a little confusing to think about, but yeah. You'd aim the rocket this way, you'd fire gases out that way for some amount of time. Our question is basically like, how long to turn on the engine? That's what we mean by burn time, right? So how long to burn the fuel, basically. Oops. use the engines, however you want to say this. That's the burn time. Okay. Now, what equation would I use to figure this out? What do you guys think? There's more than one way to do it. What's an equation I could use to immediately solve for that? Yeah, the impulse equation. That's right. Impulse equation tells us that if I take the force of the rocket, the thrust, and I multiply by the time interval, right? If I take force times time, I get, what? Change in momentum, right? So the change in momentum in this case is basically going to be, they're in opposite directions, right? So the thrust is going to be negative, in a way, compared to the velocity, which is going to be basically just m times what? V final is, I'll write it like this, mv final minus mv initial. And I'm leaving something out here, by the way, which is the mass is going to change, right? Like, the mass totally would change if you eject rocket fuel at the back. So we're not going to worry about this for this problem, but let's assume that the mass stays roughly constant and it doesn't take too much mass of ejection to actually, push it out. So this is going to be mass times V final is going to be VA, right? Because it was moving with the space station, VS, and then it needs to drop its speed to VA. Okay? And that should be equal to negative thrust times delta T. We know that the thrust in this case is equal to 10 to the 5 newtons. That's given. Not 10 times 10 to the 5, but just 10 to the 5 newtons. Right? So then what we can do now is just solve for delta T. And we're going to get basically delta T is going to be equal to the mass times the change in velocity. I think that's going to be a negative number, which we then divide by negative thrust. Plugging in our numbers, mass is... Okay, any questions as I'm writing this out? I'll just plug the numbers in. Does that look right to you guys? Okay. So that's how long it has to burn the engines. There's actually 3 questions here. And then the next part is, it's a long time, isn't it? Maybe I should make the thrust factor of 10 bigger. It's only 13 seconds, right? It's like the bigger the rocket, the less time you have to burn. Yep. So this will allow it to basically fall back down to Earth. And if it falls back down to the radius of Earth, what's going to happen is, like, effectively, once it gets to this point, it's going to interact with the Earth's atmosphere, right? And upon interacting with the Earth's atmosphere, its speed is going to slow down, and it's going to have this decaying orbit where it's eventually just going to kind of, collide into the Earth at some point. This is like the image you get if you watch space shuttles return to Earth, where when they hit the atmosphere, right, they start to burn up as they interact with the atmosphere because they're moving very quickly. And so there's some friction and drag with the atmosphere, and if that drag is high enough, the friction can make the object burn. So you have to use heat shields and stuff like that to basically make sure that your rockets, your payloads don't get damaged on the way home. But it also has the effect of slowing the object down and naturally bringing it back to Earth. Because if it wasn't for that, the object would basically just keep going around in the same orbit over and over and over again. It's the fact that it gets close enough to the Earth that allows it to actually have its orbit decay. And that's actually the way in which, in like the earliest kind of times that we sent people into space in the space program, like the first person that orbited the Earth, they put him up into orbit, and he was at a very, very low Earth orbit, and it was a low enough orbit that his shuttle was interacting with the atmosphere, but he was able to go around the Earth, I think, 7 times before he completely lost enough energy to actually start to fall down and, you know, pop parachutes and stuff like that. It's just it's a way we can slow ourselves down from outer space. Okay, do you guys have any questions about this at all? It's a pretty kind of like tricky problem. I don't know if it's that hard. I know that doing the mathematics of this in reality happens to be like working out the details. I remember when I was doing these problems when I was younger, I would mess up a lot of the math, because one of the things I would always try to do was plug in numbers too soon. You know, it can be pretty easy as long as you kind of wait till the very end to plug in numbers if you can. Watch your signs too. This thing has to be negative. This has to be negative. You keep track of which mass is which. You don't want to put the mass of the Earth here. This is the mass of whatever the object is. The velocity of the Earth in this system is basically 0. And that's pretty much it. That's how you do kind of an orbital transfer problem. It's pretty neat. I like these problems. Okay, any general questions about gravity? There's like one more of these problems we could do, but it's pretty similar to this, to be honest. Oh, whoops. One more thing. I do want to do this part. We'll call this part D. Find, so it says, there's a word missing here. It should be time. It should be the time to return to the Earth. I want to figure that out. So we'll call this part C prime or something like that. How would I calculate that? How long is it going to take for the satellite to actually get from here over to here, in case we want to be there ready to pick it up on a barge or something like that? How do I figure that out? Do I use kinematic equations? What do you think? Period. We find the period, right? And how do we find that, Jesus? Kepler's law, right? Kepler's third law says that the period squared is equal to this constant, basically, multiplied by the semi-major axis cubed, where the constant is basically, it's 4 pi squared over g? Yeah. It's basically, it's a good thing I got these notes here, so I don't have to memorize. I don't know why Kepler's law eludes me. I mean, I could figure it out, I guess, but. So it's 4 pi squared over gm times the semi-major axis cubed. What's the semi-major axis cubed? How do I find A? It's the purple orbit, right? How do I find what the semi-major axis is? Want me to refresh you guys on what semi-major axis means? Or maybe somebody knows. Is it the length of this side of the ellipse? Is it the distance from basically the top of the ellipse to the bottom of the ellipse? It's the axis times the constant. You're thinking of the eccentricity? We'd have to know something about the eccentricity there, and we don't quite yet. I mean, calculate it. RA plus RP divided by 2. Exactly. You take this length, right, and you just cut it in half. That's right. Half of the diameter. It's not the diameter plus the radius. It's RA plus RP. It's basically, you basically just take the distance, this length, basically, right here, right? From this point here over to this point here. And that gives you it. So, perfect thing. Whoever said it, it was George, who said that it's basically you take the radius at point A plus the radius at point P. That's basically the total size of your orbit, and then you just divide by 2. And that ends up being, well, okay, what's RA and RP? We know this. We can do this if we want to. But let's see, RA is 19,200, and the other one's the radius of the Earth. So it's basically, RA is the one that's bigger, right? Okay, so it's 19,200 plus RP was 6,400. Now those are both kilometers, and we divide by 2. So we end up getting, I'll do this real quick on my cell phone. So that's 12,800. km, or that's also equal to, what, 1.28. This is times 10 to the 3, so it's going to be times 10 to the 7, probably. I think. Is that like right? Yeah, 1.28 times 10 to the 7 meters. Something that's just kind of nicer about kilometers, but whatever. So that's that. We need to convert it to meters because we're going to get time in seconds, and G is in SI units, and M is in SI units, so we're required to, unless we want to convert G to kilometers, which we don't want to do. By the way, this now, let's finish the problem, then I'll mention it. I don't want to get too confusing here. All right, so that means that T is equal to, if I take 4 pi squared divided by big GM, where here M is the mass of the Earth, and I do times a cubed, then this whole thing here is going to be to the 1/2 power, and that should give me the value of T. So that is 4 pi squared over. You notice this GM thing shows up a lot, right? Big GM. I think it's sometimes called reduced mass. That's not right, it's not reduced mass. They use the symbol mu for it. If you go look up like an astronomical body on like any kind of data table, they'll basically give you the value of this because it's kind of more useful. It tells you kind of like the effects that the mass has on gravitation or whatever. So this is divided by 6.67 to the minus 11 times M, which is the mass of the Earth, which is 6 times 10 to the 24 kg. And all of that multiplied by a cubed, so that's 1.28 times 10 to the 7 meters. And we cube that, and the whole thing here we take to the square root of, or the 1/2 power. And then we get whatever we get there. Why don't you guys try to calculate it yourself? Plug it in here. Any questions while I'm typing this stuff in, feel free to ask in the chat or just ask. Yep, 14383, also what I got. Nice. So that's the period. Now, 14383. You know how much easier it is? There's a lot of disadvantages to doing this through the internet, but like the Discord interaction, I think is really nice. The fact that I can see it, what you typed, as opposed to like trying to hear it, it's pretty nice for an old man like me. Because like in class, someone will say like 14,383, and I'll get confused. Like, what was it again? 14,838? 14 or 40? Yeah, exactly. 14 or 40, that's a good. 15 or 50, 16 or 60. It was like so easy to mess that stuff up. All right, now our question was the time to return to the Earth, right? So is this the answer? Is this the answer? No. What is it, Kenny? Half. Exactly. Because we're only doing half of it. And the period is to go from here all the way around back to the same point again. Right? You're going from here all the way around back again. So we got to divide by 2. So the time to return to the Earth, we'll call it little t, is going to be t over 2. And yeah, you just divide by 2, whatever this is. 2. So 7, 1, 9, 1.5. I think 9 goes into. Is that it? Something like that? 7190-ish. That's in seconds, and of course we can convert. I think that's right. Let me do this. We can convert it to minutes if we divide by 60, right? So that number, 7191.5 divided by 2. No, not divided by 2, times 2. Divided by 60. That'll give us 120, about 120 minutes. What is it? 2 hours, basically. So this is like 120 minutes, which is approximately 2 hours. It is 2 hours. What am I saying? It's basically 2 hours. It's a long time. Space travel, just like flying through the air, it takes you time to get from place to place. It's a little different too. Because if you fly from one point to another on the Earth, like you take off, you land, right? You're under the force of gravity the entire time. In this, gravity does all the work for you. You literally think about this, like to get from this point in space back to the Earth, right? All you have to do is just slow down a little bit and let gravity take you the rest of the way. It's amazing. Gravity we can use gravity to do all kinds of really cool things. That I might talk a little bit more about that today too. Like, we use gravity to basically like fling objects out of our solar system. Did you guys know that? Because of the fact that gravity can basically change your trajectory. By coming really close to a body like this, you get this huge velocity, right? And what you can do is you can use this to like slingshot. You may have heard about this in movies. Like they talk about it in think Apollo 13 was an old movie. They talk about it in other movies too, and other TV shows, where if you get close enough to a body like that's really heavy, like Jupiter, you can basically, Interstellar talks about it, yeah, you can basically like cheat some of the momentum of the planet in a way. You can like steal some of the momentum of the planet without altering the momentum of the planet very much by just getting really close to it and letting gravity, fling you out. And I know that when, I think it was either Voyager 1 or Voyager 2, or Voyager 1 or Voyager 2, let me see if I can find some information about this. So Voyager 1 Grand Tour. Okay. So, here it is. So, whoop, what happened? Well, we can just look at this picture. We'll read this part here. It says the Grand Tour was a NASA program that would have sent... Oh, this is not what I'm looking for. No. This is what I'm talking about. Can we just get... There we go. So here we go. Voyager 1 launch, September 1777. Or 1977. That's this one here, right? So it goes near Jupiter, gets a kick of energy from Jupiter, and then it goes near Saturn, gets a kick of energy from Saturn, and then it launches out. Voyager 1, by the way, was the first... It does kind of look like a spiral, right? It happened to be based on, like, the launch time, I guess, was like... Okay, wait. Voyager path. 1 second. Let me just make sure that this isn't... Did it actually happen, though? Wait, am I this? One launched in 1977. This would reduce the mission time compared to a single Grand Tour over 13 years, 7.5 years. Working group, blah, 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 blah. The estimated cost of this was this. Congressional pressure combined with internal conflict recently led to the... Okay, so it never happened, actually. I could have sworn this was done at some point in time. Titan flyby. Voyager 2 for the Grand Tour. Would reach Saturn 9 months after Voyager 1, given plenty of time to decide if we should proceed with the Grand Tour. So I guess this was just an idea that they floated, but maybe the Congress wouldn't actually allow it to go through, is basically what they're saying. It says would have sent, yeah. But the idea was like that there was a perfect alignment of the planets that allowed in 1977 the possibility of doing this. And maybe in the future we'll be able to do something like this again. But the idea is you get these kicks of energy from every single one of these, and if you do it right, basically you can burn your fuel right when you're close to the planet, which due to the way that energy works, gives you the most like bang for your buck. Use it to like get out of the solar system. Both of these things, Voyager 1 and Voyager 2, basically have left our solar system at this point. They were launched in the 70s, and how much do you guys know about this stuff? I'm sure some of you guys know a lot about this stuff, especially if you study astronomy. Like, Voyager 1 basically carried with it all kinds of information about our planet, and the goal was to basically send a spacecraft, out into space that would have, information that if an alien civilization were to, learn about us at all, if they were to find it, basically, that you would have a lot of information, coming from our planet. Now, the information that was carried with it, so check this out. Oh, that's beautiful. I've never seen this picture before. Voyager 1's trajectory seen in the sky from Earth from 1977 through 2030. Wow. So it's coming this way, coming this way, coming this way. Oh, it came from here. That's the future that way. Okay. Huh. That's neat. So, oops. Let's close this. So what am I looking for here? I want to show you guys the golden record. I think it's on this thing. There's these plates. Okay, this is the golden record. So check this out. So this is 2 phonograph records that were included with both Voyager spacecrafts. They record sounds and images to portray the diversity of life and culture on Earth. They're intended for any intelligent extraterrestrial life form who may find them. The records are a sort of time capsule. So Sagan noted that the spacecraft will be encountered in the record played only if there are advanced spacefaring civilizations in interstellar space, but launching this bottle into the cosmic ocean says something very hopeful about life on our planet. Here's the contents of the record. I want to show you what music is on there. It's literally music from... So there's greetings, like spoken greetings in all these different languages. And there are, so ancient Greek, greetings is just like the different greetings that they have on there. But it also has music. Here's the music. So Bach, Brandenburg Concerto, so there's all these, something from the Congo, something from Australia, Johnny Be Good by Chuck Berry. Do you guys know that song? It's in Back to the Future. It's one of the songs that, like, Ricky, whatever his name, Marty McFly sings in Back to the Future. Melancholy Blues. I find this really fascinating. Like, that we actually put music in space. I think it's really cool. There's a Navajo Night Chant, which is like a traditional... That's really cool. Your kids are gonna love it, dude. I know you've seen it. Thank you, Nate. That made me laugh. It's a good quote from Back to the Future. Alright, anyway. Gravity's powerful. We can use it to our advantage. We can use it to send things out into space. And, you know, it's one of the most interesting things I think, you know, we're doing these days is the space program and exploring space, looking for new planets, all that kind of stuff. Okay, so that's the end of that, and I'm now going to kind of move on to, that's the end of our kind of discussion about the orbital mechanics and stuff, and the next thing I want to do is talk about dark matter. So, do you guys have any questions in general or comments? I wonder if I can find the plates. They also included within the Voyager, maybe it's Voyager 2? Here, one second. Voyager plates. I think it's golden plates, maybe. Yeah, it's stuff like this. This is one is so it's 116 photos picked to explain our world to aliens. This is one of them. So it's an image of a man and a woman. I think this is like a terrestrial like map of where we are. This is the transition of hydrogen, binary equivalent of the decimal, all this kind of stuff. All this stuff is inside the here. We can look at all of them. What is going on over here? Oh, is this one of the pictures? Maybe that's one of the pictures. Oh, is it you have to play it? I thought there was going to be like a list of images. Yeah, getting kind of distracted. Alright, so the last topic I want to do today, and this is going to be a short class today, but is dark matter. I don't know how long it's going to take to talk about this, to be honest. What do you guys know about this? It had a record, and it had a record player in it, by the way, Ash. It has a record player in it. They sent one with it. All they gotta do is turn it on. And I think the record was like playing music for a while, but they had to turn it off. It is pretty neat, too. I think it's pretty neat. These days we'd send like a little drive, like MP3 player or whatever, like, we'd send a little... Is the record player gold too? I don't know. I don't know if it is. And I don't know if it's actually gold or if it's just... I don't know. Maybe it is. It breaks the laws of conservation of matter. Maybe it does. I don't know. Let's see. We'll talk about what it is. So I'm gonna pull up. Well, no. Let's just put it this way. Let's talk about what the issue is. And so there was this equation we used a second ago, and it's directly related to what we're about to do. I said that for a circular orbit, right? Let's copy this real quick. If I got a circular orbit, right? This equation basically describes how that circular orbit works. Now, let's talk about the planets in our solar system, okay? And let's say that we were to plot this curve right here. And let's also say that, effectively, most of the planets in our solar system are rotating in effectively circular orbits. They're not. I mean, a lot of them are highly elliptical orbits, etc., but it's a good enough approximation as to what's actually going on. So what that would mean is I could basically take this function, right? And I can plot it. And I can plot on one side over here, velocity of the orbit, and over here I can plot the radius of the orbit. And you guys know exactly what this curve is going to look like, right? G is a constant, M is a constant, so it's basically V is proportional to 1 over R, which is basically like a curve like Y is equal to 1 over X, right? Which you guys know that's this asymptotic curve, and it looks something like, oh, not like that. Kind of comes down like this, and then it's too much. Kind of comes down like this, and then it asymptotically approaches 0. The implication is that the velocity of objects that are close to the sun, now in the middle here, we've got our sun right here, right? That's the sun. And orbiting the sun are all the different planets, right? And, somewhere close by you're going to have, like Mercury, and Mercury's pretty close to the sun, so it's going to be moving, kind of fast. And then you come to Venus, and Venus is, again, pretty close to the sun, so it's moving pretty fast. And then the Earth, and Mars, and... But Mars, since there's 2 M's. And then now you get out here. Jupiter's quite a bit farther out. Jupiter, I think we said was something like 12 times as far away as the Earth is. And then, keep going. So, Neptune, and then we can even throw Pluto on here because we don't have to be 1, 2, 3. I missed some planets, didn't I? I missed Saturn. Saturn would be somewhere in here. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Pluto. 1, 2, 4? I'm missing one, aren't I? Oh, it's Uranus. Is Uranus in between Saturn and Neptune? Yeah, it is, right? So, put the U down here. Uranus, Neptune, Pluto. Yeah, that's the order. So, if you were to go and look at the distances from the sun, that's what this R represents, right? Distance from the sun, and you were to look at the velocities, the planets in our solar system would fit very nicely on this curve. And it's kind of confirmation in a way that, you know, Newton's theory of gravity is pretty good, and that Kepler's law is pretty good. That, you know, Kepler's law's third law, like, in particular, is what led us to understand exactly what was going on. So this is in our solar system. Okay. But what happens when you look at the Milky Way? So what you would expect if you were to look at the galaxy, first of all, what do we know about our galaxy? One thing we know is right at the center of our galaxy, there's this big, heavy, massive object that holds the galaxy together. And do you guys know what it is? I'm sure a lot of you guys know. What's the thing at the center of our galaxy that's holding it together? There's a black hole right there, right? So we've got a black hole. What's a black hole? Well, a black hole is something that was theorized to exist by Einstein that is basically so massive that even light cannot escape. And that's kind of a misnomer, but it's effectively true. Information can actually escape the black hole in various ways through what's called Hawking radiation, but we're not saying that it's so massive that not even light can escape is more than satisfactory for saying what a black hole is. And that's what we call it black, is it's not actually emitting light, which is also a misnomer because it emits X-ray radiation, so it's like, yeah. Regardless, the point is that it's effectively black, and you guys probably know a couple year or two ago, I think it was last summer, that we actually got a nice picture of one of these with a lot of different telescopes pointing information at it and picking up as much data as they can on the very little faint radiation that actually occurs out of it. And we got this beautiful picture that showed up in papers and across, you know, Google News and all the different things, right? It'll probably be in, you know, physics textbooks in the future. So a black hole is an object that is capable of holding together not just a solar system like our sun does, but an entire galaxy full of stars, and a galaxy full of solar systems, right? Because the Milky Way galaxy itself is full of, what is it, millions and billions of stars or something like that. Each one of them has their own planets. But the black hole is so massive that it's capable, its gravity alone is capable of holding together all of this mass. Now, when we go to do the same thing, right, we would expect that if we plot velocity versus radius from our black hole at the center for the Milky Way galaxy, we expect something kind of similar. It wouldn't be exactly similar because now there's some issues where kind of the farther out you are, not only do you enclose the mass of the black hole, but you're also enclosing the mass of all the stars that are inside of your radius. So it's not exactly going to be this simple, but whatever. There's going to be some kind of relationship, and it's going to be kind of similar to this. Yeah. But here's the thing. If I go and plot where every single galaxy is, you know, some of them are going to be right around the right edge, okay? But the reality is, when I plot all of the different stars in the galaxy on this picture right here, they actually kind of come up like this. The ones that are close to the center, well, they're not really moving nearly as fast as they should. And the ones on the outside, well, they're moving way faster than they should. And not only that, but the curve itself is really weird. If I was to run, like, do a fit to all the data points, it would actually look more like a straight line now. This is the data, okay? And the black is the theory. And what's the theory? Well, the theory is Newton's theory, or even Einstein's theory. Both theories predict the exact same type of fact. And that is a complete mismatch between what the data shows us and what the theory shows us, right? In spite of the fact that within our own solar system, the planets actually fall perfectly along exactly where they should be in terms of their velocity as a function of radius. The ones closer are going really fast, and the ones far away are going really slow, right? And that's in keeping with Kepler's second law, too, right? When you're close to an object, you go fast. When you're far, you go slow. So this is a huge problem in physics. And in the 1960s or 70s, some scientists started to notice this. Okay, how do they get this information? You might ask, right? Well, I'll pause for a second and just show you that I'm not just making this up. So we call these galactic rotation curves, and this is a more exact explanation as what's going on. And I actually didn't do it nearly as much justice. So what is this picture showing us? This is the spiral galaxy Messier 33. The yellow and blue points are with error bars. And I predicted one from a distribution of the visible matter, the gray line. Now, I told you the curve was supposed to look like this, and it actually looks like this. This is expected from visible disks, so I kind of lied to you a little bit, but I was trying to just like paint a picture. You can notice that the curve should fall off, right? This is the key thing here. The reason why the curve rises here is due to the fact that there's a lot of matter here that's not accounted for in the equation that I gave you. Point is, this is what they expect. The velocity of the stars should get bigger, but then it should definitely fall off the farther you get away. And look at the distances we're talking about here. 40,000 light years. Light year is the distance that light can travel in a year. It is extremely far. You expect the farther out you are that the stars are moving not as fast. But the reality is that if you look, and look how precise these data points fit, by the way. I mean, it's beautiful, isn't it? I mean, I find this beautiful. Seeing data points line up with their error bars, right? The whole point of these points is that basically the line just has to go through the error bars. It doesn't have to actually fit the points, but this line perfectly goes through every single error bar. And it's this nice smooth curve, really, right? So these are the observations from starlight, the observations from 21 centimeter hydrogen. What they're measuring right here, basically, is something called a Doppler shift to the spectrum of hydrogen that you see. And this is something that, it's gorgeous, isn't it? Do you guys know about this? This is where I'm going to have to start telling you some details about cosmology and physics that you may not know yet, but I think some of you probably know this. In order to gauge distance in the cosmos, okay, there's several ways that we can do it. One of the, yeah, that's a good way of putting it. They use the hue of the light to see how far away. That's exactly right. We know exactly the type of light that hydrogen emits, okay? Hydrogen emits light that looks, it's very, very specific, okay? This picture does a really good job of describing what it is. The emission of, it's not a picture shoot. I just want to look at this picture right here. This picture is on the wall in spectroscopy, that's right. It's on the wall in physics, the 1C classroom, right? Oh, here's a good one too. So what we see here are two different things. On the top is what we call the visible spectrum of light, right? You have your red, your orange, your yellow, your green, your like blue, light blue, and then dark blue, and then purple, indigo, whatever you want to call it, and violet, right? You did this in astrobio in high school. That's really nice. I wish I had an astrobio class in high school. So when light is emitted by hydrogen, and you pass it through something, a device that we call a spectrometer, this is what you see, okay? When the light comes specifically from hydrogen, you get a 410 nanometer line, you get a 434, these are very specific, they call them the bright lines of hydrogen, okay? And it's literally a signature of what hydrogen looks like in our universe, right? So what they do is, they look at these galaxies, and when you look at one side of the galaxy, let's say that the galaxy is rotating around like this, right? When the light from the stars is being emitted by a star that's moving away from us, okay? When it moves away from us, there's an effect called redshift that occurs. And what that means is that basically on our spectrum right here, this line that was normally at 656, it might shift over to like 680 or something like that. Depending on the amount that it shifts, and they all shift, by the way, depending on the amount that they shift, we can get a precise measurement through the Doppler effect of how fast they're going. And this is how we track how fast galaxies move. It's how we track how fast hurricanes and tornadoes move. We use the Doppler effect. Have you guys ever heard that before, like the Doppler Radar? It's not used a lot around here. When I grew up in Oklahoma, storms were a huge deal, right? And they use something called Doppler Radar. Well, what they're doing is the same thing that a policeman on the side of the road does, where they shoot a beam of energy at you, a light beam, right? That light beam bounces off your car, and due to the bouncing effect, the light gets shifted a little bit, and when it gets read out by the speedometer camera, the speed gun or whatever they use, it tells you how fast it's going. And we do the same thing here with galaxies. So we look at a distant galaxy, and we say, oh, what color is it? Does it move? Is the light being redshifted? If it's being redshifted, it's moving away from us. If it's being blue shifted, it's coming towards us, right? And we can use that to get a precise understanding. And that's why it says observations from 21 centimeter hydrogen. This would be the 21 centimeter hydrogen line or something like that. I think I'm getting this right. So there's a problem. Getting back to dark matter. All of these objects out here, all of these stars, every one of these data points represents a star. They're moving significantly faster. Probably order of magnitude faster, right? Like down here, you're probably at about 25. Up here, probably at 150 or so. I mean, that's a huge difference. Like the ones on the far out part are moving like at least 6 times as fast as they probably should. Does that make sense? They're moving way faster than they probably should. Okay? And how do we explain that? So let's think about this from a different perspective, just for a second, to give you guys some understanding of this. Where'd my OneNote go? So I want you to think about merry-go-rounds. And I'm talking about the ones that you ride on in parks. Okay, the ones where you've got like a cylinder like this, you've got a rotational axis that it can rotate on, and then you've got these basically like you've got a handlebar like here, you got a handlebar here, and you've got a handlebar over here, etc. Right? And what happens is the entire system is pushed around like this. I'm talking about and what you do is you stand over here. At least I don't know. This is what I did as a kid. And you put your feet down like this, and you hold onto the bars, right? And as it rotates, what do you feel? You feel your arms tense up. You feel like you're going to be thrown off if you can't hold on to the bars, right? You guys know what I'm talking about? This picture kind of... The faster you rotate, the harder you got to pull, right? And that's because your inertia basically wants to carry you off of the device. And you got to hold on hard and exert a big force to deal with that centripetal acceleration pulling you toward the center. If your hands are too sweaty, you're going to slip off. If you don't have strong enough arms, you're going to fall off, right? Well, basically the same thing is going on with these galaxies, is that in the galaxy, so we got like our galactic bulge here, and we've got our galaxy that kind of like on the side kind of looks like this, These stars that are out here, inertia is basically just massive objects tend to move in a straight line unless acted on by an external force. Things tend to keep going in straight lines until you have a force acting on them, basically. Things move with constant velocity that's inertia. So, if you have an object over here and the velocity is too fast, then you need a force. Just like you need a force at your arms here to hold it in. So you need basically a bigger force, right? You need more force to prevent it from escaping the galaxy. Does that make sense? The velocity is too fast, so you need more force to prevent the stars from being flung into the galaxy. So where's it going to come from? Well, we're limited on the number of forces we can put into systems. We only know about 4 of them. We talked about them on the first day of this class. They are gravity, electromagnetism, the electric force, the magnetic force, and the strong force and the weak force. Those are the only 4 that we have so far that we understand that actually exert forces on things. So the answer that we've come up with is this. There must be more matter than we can see. More matter than we can see. Yep, so we assume that there are more bodies exerting gravity than what we at first thought existed. That's exactly right, Ash. Yep. There must be something else. So there must be more matter than we can see producing extra gravity, effectively. So if this is our picture of a galaxy where you have the black hole at the center and then you've got little stars all dotted throughout here and they're all going around in a circle, and it's commonly, we think of it like this, then what we now say is that the entire galaxy is actually embedded, okay, in a halo of dark matter. It's starting to look like an eye, actually. They call it a dark matter halo. Halo like an angel's halo. That's bad. Dark matter halo. Because we believe that it's diffusely spread out. It looks like the eye of star. That's exactly what I was thinking, actually. The energy, the dark matter, we believe, is spread out uniformly throughout our system, and uniformly we don't really know. It's somehow spread out throughout our system, and for whatever reason it's dark. We can't see it. And that's dark matter. It's our modern theory that we use to describe something we don't understand. And I will mention, and this is really important, this is a theory. I mean, it is a theory that is not yet confirmed yet, other than that we understand that there is some gravity that's there that we can't quite account for. You know what I mean? There is some gravity that's there that we can't account for. But here's the thing about this that's really crazy. If you actually go out and measure, okay, how much normal matter there is, stars, okay, so normal matter, dark matter, probably going to get exactly the ratio wrong, but with, so normal matter, what do I mean by this? Well, we'll talk about it in a second. Something like 20% is normal matter, and like 80% is dark matter. Whatever it is, if in fact it is a real thing, it is what the galaxy is in a very real way. The galaxy isn't the stars. It's made up of stars. But the primary content of our galaxy is dark matter. And not just our galaxy, all galaxies. Every single one of them. Every one that we look at has the same phenomenon, that the velocity of these stars on the outside are just going way too fast, and the only way we can think that they can be going so fast is due to gravitational force, basically. Have they discovered a sample of dark matter? That's an excellent question. You'd think if this stuff exists, and there's so much of it, certainly we can go and, you know, get a scoop of it, right? And see what it tastes like and touch it and do tests on it, right? Unfortunately, there's a lot of problems with detecting it. It's extremely hard to detect. I'll talk briefly about some of the ways they've tried to detect it, but it's extremely hard to detect. And the reason why it's extremely hard to detect is because this, whatever it is, okay, so like, this is the question now, what is it? Is it like a bunch of neutrons? No. Is it some particle that we know already exists? Like, for example, there's a particle called the neutrino. We don't think that's what it is either. So whatever it is, it doesn't emit or absorb light of any frequency. That means it doesn't absorb or emit like normal light, visible light. It doesn't emit X-rays. It doesn't emit thermal radiation. You guys have seen in movies where people put on like the thermal goggles and you see like the colors of like what's hot and what's cold. It doesn't even do that. So any type of telescope that we use to try to like understand this stuff, it won't work. In fact, yeah, I got some questions here. One question is, would it be possible there's a fifth force instead of way too much matter that we observe? Yeah, maybe that's right. It could be the case that, and then as Ash said, perhaps our laws of forces aren't valid anymore. Or not complete, right? It appears to be the case that our force laws work pretty well on certain scales, but when we go to this galactic scale, we start to see some issues. And we have to correct the rules. Now, there are ways to explain this without using dark matter. There's something called modified Newtonian dynamics, other ways to do it, other ways that people are working on. And I think in reality, what's going to happen is that something about our laws of physics is probably going to have to kind of be fixed, or we'll actually find dark matter someday, okay? But this is the thing that's really important for you to understand. It doesn't emit or absorb light of any frequency. It's not charged in any way, okay? It carries no electrical charge. It has to be neutral. And this is really hard for us, because we have no idea how we're supposed to detect something that has these properties. One of the things that we think we can do, isn't all matter composed of charged particles? Yeah, except for dark matter. Yep. And then what do you mean by matter? If by matter you mean what we call baryonic matter, which is to say things like that are on the periodic table, then yeah, everything on the periodic table is composed of charged particles. Yes, you have neutrons, but neutrons are composed of quarks, which are charged. And the fact that things are charged means you can see them. Electrically charged objects can interact with photons, and therefore can be seen. Dark matter does not have the ability to interact with photons. It also doesn't have the ability to interact with any of the other known forces in the universe, except for the Higgs boson. It's kind of like black bodies. The black bodies emit all energy, like they, whatever. I'm sorry, I'm sorry. Okay, so carries no electrical charge, it's hard to see. So how do we see it? People have come up with all kinds of ways to look at seeing this thing, and I'll mention to you guys some of the ways they've done it. When I was in school, this was back in about 2010. At that time, I went to several conferences where they would talk about projects, and the way that these projects would work is they basically take a box, okay, And the box will be filled with some type of a crystal. Okay. So in here you have, like, some crystals. Or you have, like, some densely packed substance. I think they use liquid xenon in one of them. I don't know. You've got some kind of a crystal inside of here, right? And surrounding this crystal is a bunch of what are called photomultipliers and detectors, stuff like that. So what they're hoping is that a dark matter particle, we'll call it just DM. Well, let me mention some other things about this. Because of the fact that it doesn't absorb or emit light and carries no electrical charge, the way we understand it now is that if you were to look around your room right now, supposedly there's dark matter all over the place. And it's basically passing through your body all the time because it doesn't interact with anything. It's all over the place. If you swung your hand through the air, you would certainly pass your hand through some amount of dark matter, right? So it's all over the place, and we believe that basically it can effectively smash. It could even be in your room right now. That's right. So the dark matter basically, we believe, can basically pass through things completely. But they still want to try some type of an experiment where they think that, suppose that this crystal, as it's passing through space, it interacts with a dark matter particle, and they hope that basically what would happen is the crystal is going to vibrate in some way if the dark matter actually directly interacts with the crystal, and that this vibration back and forth, this wiggling that occurs right here, can output some energy in the detector that they have right here, and they can use that to find evidence of dark matter. And so they take these crystals or these liquid xenon things, they put them in a deep, deep mine underground in Italy, and yeah, they try to observe if there's any interaction with some kind of a dark matter, and if they could have a signal for what it is. I'm not talking about entropy right now. Nope. Just talking about how we can see something like this. Now, I don't believe any of these experiments are ever going to be effective, because if what we know about it is true, I don't know how they actually think the dark matter particle is going to interact with this thing. Because it has to interact through a force. The only way particles interact with each other is through forces, right? And if this object doesn't interact with the electric force because it's not charged, and if it doesn't interact with the weak force because it doesn't carry any weak charges, or the strong force because it doesn't have any color charges, then the only thing that it can interact through is gravity. And gravity is so incredibly weak that it's like, it's not going to... That would be like this object would come close to the crystal and be deflected by the gravitational energy of the crystal, and that's just not going to happen because the gravitational force is so incredibly weak. The reality is, I think, that this dark matter particle is going to do exactly as I said, and it's just basically going to pass right on through, leaving absolutely no energy in the detectors that they're creating. So that's one of our modern ways. We call this a this is called a direct detection of dark matter experiment. There's other methods too. One of the other methods is, by measuring galactic rotation curves, or indirect measurements. Now, there's one other way that we try to detect these things, and this is what I worked on when I was in grad school, which is, well, if it's something that exists in the universe, maybe we can produce it at a collider. A collider is a place where, right now at the LHC, we send two beams of protons at each other, and those proton beams collide, and then out of the collision, so much energy is located in one place, like 14 tera-electron volts, that you can basically produce all kinds of things that only existed for even brief moments right after the Big Bang, such as the Higgs boson. That's one of the things they discovered there. But one of the main things that they were really hoping to discover at the LHC is they wanted to actually find the dark matter particle. Because within the world of physics, we have all kinds of good, what are called candidates for dark matter. One of them comes from a host of different theories, one of which I'll refer to. Supersymmetry. Supersymmetry says that there are basically, for every regular particle we have, like the electron, there's something that's called the superpartner. And that superpartner happens to have a couple different properties. First of all, I think it's... Oh man, I'm forgetting one for a second here. I think it's... Well, we call it the selectron. It's the superelectron. Okay, and the way in which these are different from each other, I think we use this symbol for it, E with the tilde above it. These guys are a little bit different from each other. I think they have the same charge. That part I don't remember exactly. What I do know is that if this has a spin that's equal to 1/2, this has a spin that's equal to 1. Which is just to say that these are what we call fermions that have half spin, that have certain rules about them, and these are what we call bosons. Literally call it the selectron, which stands for superelectron. It's heavier, it's different, etc. This theory that we call supersymmetry states that for every particle that we know about, there's a partner particle, okay? And one of those particles is called the neutralino. This is a combination of a bunch of different states, and I don't want to go into a lot of details about it, but to say that it is one of the particles of supersymmetry. And this particle is what we call a dark matter candidate. It has just the right properties to be dark matter. And we're hoping that in these collider experiments one day, we'll be able to find one of these things. But it's extremely difficult, because the way that they show up in your experiments is what we call missing energy. You calculate the initial energy of your system, the final energy of your system, and if you have missing energy, then it's possible you produce some of these things. But it's inherently problematic, because it's missing. It's data that's not there, right? So you're still at that same problem of, well, things are moving too fast, and we can't see what's doing it, but we call it dark matter. We say, well, maybe we can design an experiment where we can produce these things and then prove that we found dark matter. But the problem is, the only way they're going to show up is that we don't detect them. You guys see the inherent problem here? The only thing we know about this stuff is that we can't detect it. And that's inherently problematic for science, which is all about detecting things and measuring things. We cannot measure this thing. It defies all measurement. It defies all attempts to do science on it. Right? Because science is ultimately about taking a ruler and measuring how long something is. And it's all about, you know, measuring the decay rate of certain particles. And it's all about measuring the spectral lines of hydrogen and using that. But, like, you guys justified it with something which doesn't have qualities of existing. Pretty much, Ash. I mean, this bothers me more than almost anything in science, because it's extremely well-founded that you need something like this. And I haven't even shown you all the evidence of it. You can go and read for yourself what all the evidence is. There's evidence of the way that there's something called a bullet cluster. Yeah. You can go read about it yourself. But the bullet cluster basically is a situation where we see two galaxies colliding with each other, and it appears as if the matter is in one location, the mass, and the light's in another location. Okay. And it's just like more evidence that this stuff like almost has to be real. Or our theories are just wrong. Or our theories are just wrong. You know what I mean? And we're at the precipice of finding a new understanding about the universe. And a new understanding about what these kind of things can do for us. We've been looking for this stuff for quite a while. Almost 60 years now or something like that. People have been working on all kinds of theories. This theory of supersymmetry is not the only one that it produces dark matter candidates. You can use what are called extra dimension theories, where you basically add dimensions to the universe, and you can use those to produce what we call a dark matter candidate. Now, I say candidate because it has to have all kinds of certain properties. One of the most important properties that dark matter has to have is it can't decay. It has to be a stable particle, okay? What's a stable particle? Well, this is a stable particle. Electrons do not decay, as far as we know. You guys know of any other stable particles in the universe? There's not many of them. There's not many. There's very few stable particles that exist in the universe. Particles that can't decay. Do you guys know of any? Yep, that's one of them. The proton is one. What else? The electron is another. That's it. That's the list. That's basically it. I think the photon's one too, but the photon can do weird things. I think you'd put the photon on here too. I think. Kind of. It's different. Yeah, it doesn't have mass. It can't decay. Yeah, the photon's a bad one. Bad example. The proton, that's it. That's it. That's the freaking list. That's all you've got to work with is protons and electrons so far. We're looking for a brand new particle that is as fundamental to the universe as these two things. These two things compose all stars. All stars are just a big gas of protons and electrons. That's what they are. They're just big plasmas. Photon is a particle. It just doesn't have mass. That's true. So the third one on here is dark matter. And we don't know what it is, but we know it can't decay. Or that whatever it's doing, it's constantly decaying and recreating or something. We don't really know what's going on with it. We just know that it has to be like the proton and electron. You have to set up something in your theory that once you produce these things, they never disappear. Ever. They cannot ever they can never disappear from the universe. The neutron can decay, by the way. Uranium can decay. The nuclear, this is how it works. You know, carbon-14 can decay. Protons and electrons can't. They are constant. They are universal, like, they don't go anywhere. Anyway. You guys have any questions about all this stuff? I mentioned it to you because, yeah, exactly. That's why I'm talking about this, Ash. Exactly that. That's almost exactly what I was about to say. Physics seems to be this theory, and I believed this when I was growing up, that felt so perfect and so complete, and I wanted to study physics because I wanted to know more about the universe, and I wanted to understand more about the smallest things in the universe, particles, the largest things in the universe, galaxies, and black holes, and those kind of things, right? And I really thought, when I was going to study it, that I was going to go learn all the answers. But the truth of the matter is that at the cutting edge of physics research and chemistry, biology, everything, is that there are still so many problems left to solve. And this is a big one. This is a huge one. Gigantic is the word you used, Ash, and I agree with that. It's a gigantic problem that is fundamental to our understanding of science. It goes back to Kepler. Like, Kepler would have seen this and said, yep, works out. That's how Kepler figured out that there was, he didn't see this relationship, but he knew that there was a relationship between distance and period, right? Or in this case, this is velocity. You can't see it over here, but that velocity is related to period. Yeah. Kepler's law, right? And in order to fix Kepler's law, the only thing we know to do is to add more mass. And, you know, that goes back to one of the first true theories we had about the universe, the relationship between how the planets move around the sun and their distance. And it feels like it's worked forever, but it seems like it kind of falls out because of the need for something like dark matter to solve this problem. Yeah. Do you guys have any questions about this? Show you guys what some of these I remember seeing plots like this when I would go to conferences. So all we've been able to do is rule out phase space, and there's all these different experiments going on. This is so hard to read. I remember seeing this plot for the first time and just being like, oh my god, what's this? And they're trying to pin down what the mass is, but it's just this gigantic phase space, and they have no idea how to get it. Ah, here you go. Here's a nice picture of one of the direct detections. This is at Stanford. Particle comes in, it hits something, it moves on, and then electrons send energy, and then they get picked up by what are called photomultiplier tubes. That's how we detect it. Yep. Okay, I'm going to stop the recording right here. We'll stick around if you guys have any